Yeah, now we are speaking about torsion equation for circular shaft. Here TR is nothing but torque, where J is polar moment of inertia, where this is shear stress, where R is radius of the circular shaft, and this is a solid shaft, and where G is the of uh, modulus of shear stress, where theta is twisting angular twist, where L is length of shaft. Now let us take a shaft, and this is the side view, where this is the radius, this is length of shaft, and now let us say this is the longitudinal axis. Now what we do is we apply torque, twisting moment, and by this there will be a change in this longitudinal axis to new position at the free end. This is B dash. So finally what we get is shear strain, that is phi. Phi is equal to shear strain. Now let us go into the derivation. We are going to derive a torque by polar moment of inertia is equal to shear stress by radius of the shaft is equal to modulus of shear stress into theta twisting angle by length of the shaft. Now let us do the step one by one, and first of all let me draw again the same figure. This is AB, longitudinal axis. Now after applying the torque, it occupies a new position at the free end, that is B dash. Now let us use some trigonometrical properties, where this is phi and tan phi is equal to opposite side by adjacent side, which is nothing but equal to B dash by length. And as we know that the twisting shear strain is very small, as tan phi tends to 0 implies tan phi is equal to phi. So phi is equal to B dash by L. Now observe it carefully. Let us make this as a 1, equation 1. Now since we know the side view, it will appear like this. This is O and this is B, and this is the new position after the torque. The B moves to B while applying the twisting moment torque. So we know theta is equal to arc by radius, and arc is nothing but B dash in this case, and theta is the twisting angular twist and R is the radius. So this is equation 2, and now we are equating equation 1 and equation 2, like we are substituting B dash in this equation 1, and we get phi is equal to theta R by L. So finally we came to one conclusion, and now let me say that modulus shear modulus modulus of shear stress is equal to theta is equal to shear stress by shear strain, where we already know that this shear strain is in equation 3. Now substituting torsion is equal to shear stress is equal to G into phi, G into theta R by L, and finally we come to a conclusion that shear stress is equal to G theta R L, and we can bring this R here, and we came to a new notation, a new equation, and this is what uh, the first part of the equation where this and this. Okay, now we are going to derive the third part, and it's a little complicated, so listen it carefully so that it will be easy. Now I am taking the cross sectional view, and I am taking the small area of that section, and let us say this is area A, and when we apply a force here, we tend to move this body. So torque, we are going to we are applying this force, we are producing torque. So force, shear stress is equal to force per area for this section, and this force is equal to shear stress into A. This is actually a small force, like the force acting in this area, so I am taking it as dF. Now what is torque is nothing but force into radius. Now this area is, let us say, a small r from the center, so this is small r. So torque is equal to dt, I mean small torque, dt is equal to df into r is equal to torsion A into r. And we know that torsion by r is equal to g theta by L, and we got a derivation before like this: df into r is equal to torsion A r. So now I am substituting this torsion here, so dt is equal to ttl into, like this is a torsion acting in that small area, so I am taking this as small r, torsion in that small area, so r a r, so dt l r square a is equal to the actual torque acting on the small area. Remember that this is only a torque acting on the small section area, not on the full. So now we have to integrate it. So torque is equal to g is constant and theta is constant, L is constant, so integration r square a. And we know this is nothing but it's in a longitudinal direction, so it is in zz, so this is polar moment of inertia. So torque is equal to g theta L by polar moment of inertia, we denote it by j. So let us say j is equal to I zz, and I am representing by j notation, so T j is equal to g theta by L. And we already have shown you that we derived this, and now finally we got a conclusion that equal to torsional stress by R. That's all. Thank you for watching it.